There we go. Thanks, James. Good afternoon, everybody. Happy April 1st. Hopefully you didn't get fooled today. I'm Dr. Noel Schultz, a faculty member at Washington State University, and I'm going to introduce our speaker today, Dr. Matt Revelle. And Dr. Revelle is going to talk about interprocedural binary analysis for automation and computer-human collaboration. A little bit about Dr. Revelle. He's an assistant professor of computer science at Montana State University. He joined there in the fall of 2023 and previously worked as a senior principal research scientist at Kudu Dynamics in Boulder, Colorado. His 21 years of computer science experience, including 13 years of computer security experience in vulnerability research, reverse engineering, program analysis, and computer network operations software development. Holds a PhD in computer science from George Mason University, where he focused on machine learning for graph data. He's also been the PI on several DARPA programs in developing, and his teams have developed automated analysis techniques for discovering and reasoning over software vulnerabilities. He has started at Montana State University, the Harnessing Automation and Cybersecurity Reasoning Lab, which he supports undergraduate and graduate students and mentors students. His current research includes the development of novel program analysis and machine learning techniques for cybersecurity tasks such as vulnerability discovery and exploit development. So, Dr. Revelle.
Oh, thank you. I didn't realize it was so long until hearing it read back. But thank you very much. So my name is Matt Revelle. And we'll be talking about interprocedural binary analysis. The general outline for the talk is I want to first kind of introduce the vulnerability research kind of workflow through an example, and we're gonna kind of jump right into that. And I'm hoping that I'll do an adequate job describing that workflow for folks that are unfamiliar with it. And then as we go on, I also hope that you'll see kind of the connection between the automated analyses that we're going to be discussing and how they can help assist that workflow. We will then be talking about this notion of representing programs as graphs. And when we have this graph representation of programs, it can get really complex. And so one of the things and kind of the bulk of what we're going to be covering today is showing how constraint-driven transformations can simplify those graphs. And then we will also be touching on using type inference in binary analysis. So this type inference both kind of helps support that constraint-driven transformations that we'll discuss, and also has some interesting use cases separately from that. So our example. So I've mentioned reverse engineering and vulnerability research already, and I kind of just want to give a definition of those for those that are unfamiliar with those terms. So reverse engineering is the task of figuring out how something works, and that can be a hardware device or that could be a piece of software. And in some cases, say when we have a piece of software that's compiled, so we have an executable, but we don't have the source code. That means that we have to, in order to understand what that piece of software does, we have to examine that program binary. A related task is vulnerability research. So if reverse engineering is understanding how something works, vulnerability research is trying to identify vulnerabilities in that same something. So we might use reverse engineering as when we're conducting vulnerability research. So the example that we're going to talk about here is a vulnerability. It was a real-world vulnerability that's been reported and patched since then. And it is in this Western Digital My Cloud device. So this is a device you might use to store backups from your laptop or desktop. And the code we see here is kind of introducing at a high level what's going on in this web service that's running on this My Cloud device. So we can see there is this authentication check, and we can see this, and that's because there's been reverse engineering work that's been done ahead of time to figure out that that's what this function here is actually doing. But just to get an idea of what the structure of this program is, we have an authentication check. So there's some kind of check that's happening inside that function, and we're going to take a look at that function in a moment. And if we pass that authentication check, then we eventually we can end up executing this call to system. And this is where the command injection vulnerability occurs. And a command injection vulnerability is just when, as an attacker, we're able to insert in an additional command that wasn't intended to be executed. And the calls to system are a common way that that vulnerability is introduced in software. So the goal here from an attacker standpoint is to get some data, a string, passed into this call to sprintf. That's going to prepare a new string that has our injected command contained within that string, and then that string is going to get passed to this call to system and executed. So that authentication check, if we look at that function, we can see there are some things that we need to do in order to pass this check. So this is going to accept a username and a password. And at the top here, we see the password is expected to be base64 encoded. So that means when we were providing our input, if we're sending a request to this web service and we're trying to exercise this vulnerability, we need to make sure that our password is base64 encoded. So once we get through that check and we have our password correctly decoded, then we notice something that's interesting. So there are these two calls to string compare, the strcomp function. And what we notice is that there are a hard-coded username and a hard-coded password that are being checked against. So there are hard-coded login credentials embedded in this program. So if we have access to this binary, we reverse engineer it, and we see that these credentials are included in that binary. We don't have to guess a username and password if we were trying to exercise this vulnerability on some device, because we know we have a good pair of username and password. Then we get to a point where we check to see if these are the same, and then this variable here is being used to store the result. So it's kind of you can think of it as are we authenticated? So an is authenticated variable. So putting this all together, taking a step back again, what we have is this function A, a function B, and a function C. So function A is where user requests to this web service come in. Based on the content of that request, you can see there's all these different ways that request might be dispatched to be handled and further processed. But we only care about one. So if we're trying to prove that this vulnerability exists in this device, we only care about getting to this function that we've labeled B. Then inside of B, right? So what I've marked here with this lightning bolt, that's where the actual vulnerability is. That's where that call to system is. But in order to make it there, we first have to go to the authentication function, which is labeled here in C. We have to, say we want to provide our hard-coded credentials so that we successfully authenticate. Then once we've successfully authenticated, finally, we reach the place where the call to system occurs. So this, what we've outlined here using these three different graphs and jumping back and forth between functions is locating a feasible path, of execution through the program that reaches that vulnerability using those hard-coded credentials. So manually doing this, knowing, we could get stuck looking at all these other locations as well, for example, or even just within B, like what really needs to happen in B for us to be able to reach the vulnerability. So we can automate some of the tedious aspects of that. And so that's what we're going to talk about today, because what we really want and what we can get using the techniques that we're going to be discussing is just this nearly linear path of execute. So this represents a path of execution through the program, getting from that entry point where we send our request in and it's initially dispatched to the call to system that has the vulnerability. So our problem statement, if we want to kind of just summarize what we just covered in that example. So we want to use automated analyses to interactively help vulnerability researchers manage the complexity of analyzing program binaries for vulnerabilities. And so this is, what we're going to be talking about is something that could be done, and so it has been used in a sort of an interactive fashion, where there are places where some automated analyses are very expensive, and so we might want to be more conservative in their use. However, if we have a human that says, I really care about this piece of the program, then we can deploy those, and it's no problem, because we're not analyzing the whole program. We're just analyzing the specific part that was pointed out to by a human. So similarly, what we just saw with that example is there are a lot of different branches and paths for us to consider if we were doing this this vulnerability research completely manually. So instead, we can make use of some automated analyses, such as these constraint-driven transformations, to kind of prevent ourselves from being distracted or dealing with sort of the tedious aspects of vulnerability research. So we're going to talk about the techniques, but I first just wanted to mention that all these techniques have actually been implemented. And there's an open source static analysis framework called Blaze. And that's where we took these ideas, and that's where they've been implemented. It's available on GitHub if you're interested in checking it out. And I'll throw this slide up at the end to use as a reference in case anyone's has more questions about it. So we talked about, we got an idea for what reverse engineering and vulnerability research looks like for compiled software. So I wanted to talk a little bit more about that. So what we're looking at when we're doing binary analysis is a program executable. So more generically, we can call these a program binary. But if we have a single program, we can think of that as a program executable. The things we're talking about also apply to compiled shared libraries as well. So this program executable is represented in a file format. So one of the common file formats is ELF. That's, for example, used on Linux operating systems. The notion of a program executable, right, is that it's a representation of a program that can be executed. And the term usually implies that we have a compiled program and it can be run natively on the operating system. So, for example, without the help of a virtual machine, like in the case of Java. So ELF is one of these file formats that we can use to represent a program executable. And that file is going to contain the code that that's the implementation of the program, data. So like, for example, initial values for variables in our program. And then there would be additional metadata as well. So this could be things like information about how to link our program executable with shared libraries. And on the right here, we can see a glimpse of what how the code is represented. So we have this sequences of instructions, and in this case, they've been disassembled, so we can actually see what those instructions are. This was a program executable that was compiled for 64-bit x86, and so that's what we see, that the instructions are 64-bit x86 instructions. And so this is kind of what we start with as our view into a program when we're trying to understand what the program does, is this linear disassembly view. But we can instead, from that disassembly, we can generate graphs. And it might not be immediately clear how this is useful or why this is better than that linear sequence of disassembly, but hopefully something that might help you start to see why graphs would be preferred, and specifically the graphs that we're talking about, our control flow graphs, is to consider. Here we have these two functions, func A and func B, and then on the right we have two graphs labeled 1 and 2. So func A is a really simple function. It just has an if-else statement and is doing some conditional execution based on the values of x and y. Func B, on the other hand, is receiving a collection of items and then has a for loop. So it's looping over those items. And in this case, it's computing a sum. So it might be worth taking a moment so each of these graphs match to one of these functions. So it might be worth thinking which one matches to which. And if I could see everyone better with my team set up, then I would ask this and look to see if there were any responses. But maybe just, so hopefully it's obvious, right, that func A corresponds to graph 1, right? So you can think of this is where we're initializing that result variable. And then this could be the true branch where x is equal to y. This is the false branch where that's not the case. And then later, control flow converges back together at that bottom node. Similarly, it should be obvious that once you get used to looking at programs as graphs, it is immediately obvious this graph contains a loop. And you can tell that because we have this back edge from one node to the next. So these patterns are really, so not only is it useful to kind of have this graph representation for performing automated analyses, even for humans, when we're interacting with, when we want a representation of a compiled program that helps us understand what's going on at a glance, right? We have an idea of what the control flow structure of these functions are. So what we were just looking at and what we're going to be talking about is our kind of foundational graph representation today is a control flow graph. So these are commonly used when analyzing program binaries. I would say they're one of the two main ways that we look at compiled programs, so or program binaries. So the idea is that we can automatically, based on analyzing the control flow of a function, we can take that linear disassembly and instead get this graph representation. So here, the source code on the left, it corresponds to the CFG we see on the right. And so you can see it's kind of similar to what we were looking at before, where we had that if-else statement. And so you get this kind of diamond pattern. Another thing it's worth pointing out, just as an aside, if you're curious, we're not seeing disassembly here in these basic blocks of the control flow graph, or these nodes of the control flow graph, and that's just because we can do some lifting from disassembly to a slightly higher level representation, which hides some of the complexities that we would find in disassembly. So when we're trying to understand what a program does, sometimes we'll do that lifting. And then when we actually want to test out an idea, like can we trigger this vulnerability, then that's when we'd want to go back down to have better fidelity and use the actual representation of the code that's going to be executed. So if we have control flow graphs, we can have interprocedural control flow graphs. So control flow graphs are generally restricted to, or generally used to describe a single function in a program. So an interprocedural control flow graph is where we are including we have a CFG that can span across these function calls. There's many different ways there are many ways we can represent an ICFG. The way that I've chosen to do that is by looking at individual calls, putting them into their own node called a call node, and then we can actually expand these call nodes. So for example, here we have this call to a function bar. If we expand it, what we're doing is we're taking the control flow graph for the function bar and inserting it into the control flow graph to contain that original call. So that's how we build an interprocedural control flow graph. Something else that's useful for us to be aware of are something called dominators. So dominators we're gonna use that in order to figure out which constraints are active for a given node. But first, let's kind of talk about what are dominators. So we have a control flow graph here with a few nodes labeled A, B, C, and D. And first, let's look at our definition. So a node X in a control flow graph dominates a node Y if every path from the root to Y passes through X. So with that definition, A, which is the root node for our control flow graph, right? It has no predecessors. So A trivially dominates every single other node in the control flow graph, right? Because there is every path the paths to all the other nodes must go through the root node. So a non-trivial example though would be, so we can say that B dominates both C and D, and that's because every path from the root node A must pass through B before we reach C or D. Similarly, all these other nodes that are along this path from A to B, they all also dominate C and D. A node can have many dominators. It's a generally this is a useful calculating all the dominators or calculating a dominator tree is useful for a number of analyses. But the one that we're going to be looking at today is the use of dominators to discuss dominating constraints. So we can use these dominators to identify the constraints that are active for a node in the CFG. We have this notion of a branch context. So anytime we have conditional branching, right? So up here at the top, the root node, we have this if statement. We're checking to see if arg1 is equal to 0 or not. And then depending on if it is, we take one branch or the other. We see similarly down here. So each time we have this branching happening, we introduce these branch contexts. And there's a branch context associated with each side of the conditional branch. So here, if we see that, so arg1 is equal to 0, that's the test we're performing. If we take the false branch, that introduces a constraint saying that arg1 is not equal to 0. So if it was equal to 0, we would have gone down this branch instead, and we'd be executing, our path of execution would go this way. But if it's not, then we pick up this constraint because we've entered this branch context. So similarly, if we go down all the way to our next conditional branch, we can see there's this test to see is var10, so we're testing here, var10 not equal to 0. So if that's true, this green color denotes that this is the true branch for this test. That means we've introduced this constraint that var10 does not equal 0. So those are the constraints we're picking up from our branch context for node A. So we've listed them both down here. Similarly, if there are any assignment statements that occur through this path to getting to A, so in any of these nodes that dominate A, then we're going to include that as well as a constraint. And so this var10 equal to arg1 constraint, that comes from this block down here. So there's an assignment of arg1 into var10. So that means that these values must be the same. So when we're putting together our entire sort of constraint formula that we want to test to see whether or not reaching A is feasible, we have to include that bit of information as well, right? And so we can look at this. So we say our constraint is arg1 is not equal to 0, var10 is not equal to 0, and var10 must be equal to arg1. So we can do that, right? So we could an assignment that we could just we could throw out there is arg1 is equal to 1, var10 is equal to 1, and hey, they both need to be equal to 1. So we've also satisfied this final constraint. So in contrast to that, though, if we look at node this labeled B down here, so here we pick up, we're within this branch context, so we pick up this constraint, arg1 doesn't equal to 0. Or arg1 not equal to 0. Then down here, we pick up the opposite constraint that we used that was placed on A, right? Because we're taking the false branch. So it's a different branch context, different constraint. So we have var10 is equal to 0. But we also have this assignment constraint, right? Because this node dominates B as well as it dominates A. And so we have this constraint that var10 is equal to arg1. So we see, right, so we can see, right, that var10, if we're saying var10 must be equal to 0, and we're saying arg1 can be anything other than 0, but then if they have to be the same value, right, that's not possible. That we can't meet that constraint can't be met. There is no assignment of these variables arg1 and var10 where this constraint is satisfiable. There's another way that we can say that. So because of that, we know that we can never reach B. So that's an entire, so B and everything that comes after it, we can just cut off of our control flow graph. So we can see, so if we take a step back and we consider these functions separately, so we have a control flow graph for foo on the left, and we have a control flow graph for bar on the right. So these constraint-driven transformations that we're talking about, we're using branch context to simplify an interprocedural control flow graph. And in this case, we note that foo calls bar. And so if we were to expand the control flow graph for foo by expanding this call node, so this call to bar, and we want to insert the control flow graph from bar into the control flow graph for foo, then there are some pieces that we can just immediately cut out. So if we look at in foo, we see we have this branch context where arg1 is not equal to 0. That's where this call to bar happens. And we also note that this arg1, this is the argument that's being passed into this call to bar. So that means this constraint is going to be, you can think of it as the entire CFG of bar fits under this branch context. So given that that is the case, in bar, this branch here that inserts that introduces this constraint, this branch context that says that arg1 must be equal to 0, it is never going to happen. Anytime we call bar from the function foo, this code will never be executed. This code in bar will never be executed. It can't be executed, at least not under normal operating conditions. This would not be executed. So what that means is we put it all together to try to see that big picture. So we have this control flow graph for bar. Again, we have this area grayed out here. This is what indicates the portion of bar which is infeasible when bar is called from foo. When we expand the call to bar inside of foo, you note we only have these 3 nodes or basic blocks are what we include for the CFG to bar. This part that's grayed out does not appear here because it's impossible to reach it. And so our analysis is able to automatically identify that that's the case and just remove it. So we've been looking at this simplest example with these 2 functions, foo and bar, but we've also had success running this in the real world. So we were using CBS, which is a version control system software. So if you're familiar with Git, before Git, the most popular tool was Subversion or SVN. Before Subversion, it was CBS. So I'm sure there are still some folks that use CBS, but it's certainly not the most popular option these days. But this is a function where, given the calling context, all of these nodes that are highlighted in red are nodes that would be removed from the control flow graph, right? So this is a real world case where these constraint-driven transformations can greatly simplify these interprocedural control flow graphs that we're using to kind of test hypotheses about vulnerabilities in program binaries. One of the things that enables these constraint-driven transformations that need to be mentioned is something called SMT, or satisfiability modulo theories. So if you are SMT solvers are kind of they're related to SAT solvers. So that's where you have if you're familiar with the problem of Boolean satisfiability, where you have a bunch of Boolean variables and you're trying to determine some assignment to those variables in which some formula or some constraints can be met. So SMT takes that concept and extends it to support things beyond Boolean values. So the modulo theories part, the theories is what is referring to different types of values. So an example here is on the right, on the top right, is an SMT formula or program, if you will. We are defining two symbolic variables, x and y. We're giving they're both of type int. Then we have these three assertions we're adding. So these are constraints that we're adding on our variables. So we're saying x must be less than 10, y must be greater than 0, and then finally a constraint that that relates x and y to one another, where we say that x must be equal to 2 times y. And then on line 6 and 7, we can check for the satisfiability, and then we can get a model. So a model would be an instance or an assignment of the values to those variables x and y that are satisfiable, that do satisfy these constraints. And so we can see when we request that, we get back an assignment that y is equal to 1 and x is equal to 2. So behind the hood, an SMT solver is being used. So the step that we're taking is we have these constraints that we're recovering from the interprocedural control flow graphs. We sort of translate, or you can even think of it as compilation if you want to, those constraints that are expressed in terms of an intermediate language that we're using to describe the instructions that are being executed. So that's when you go from the disassembly up to a slightly higher level representation. So that higher level representation is something that in the Blaze implementation of this technique is a language that we call PIL. And so those PIL statements and expressions are being converted to SMT formulas. And so then an SMT solver is then reasoning about that for us and letting us know whether or not this formula that we've constructed is satisfiable. So one thing that I wanted to fit in is that conversion from our PIL statements to SMT formulas. I just mentioned how SMT supports different types, and that's what gives it its that's what makes it more flexible than using a SAT solver. However, that does require that we know the types of things, right? So if we're taking a program binary, and everything kind of starts off at that level, one could even argue that do we really have types, or should we be thinking about everything as being a bit vector, right? So a bunch of bits or bytes. But if we want to do reasonable, if we want to make our reasoning feasible, we want to try to recover the type information from for that program. And so to do that, we introduced we have a type system that comes with PIL, that intermediate language that is used by Blaze. And here you can see just a table describing the different types that are supported by PIL. And then this thing, if you haven't seen this kind of thing before, I'm sorry, because I know it does not. It might not convey that much information to you right away. But this is something that's called a type lattice. And it's useful because we can see the relationship between different types in our type system. So in this case, how you can read this is, so this type here, bitvec, represents a bit vector of some width or some length. All these relationships, these lines going down, everything that's below that bit vector is a subtype of bit vector. Right, so you can think of all bools are also bit vectors. All Boolean values are also bit vectors. All integers can also be viewed as bit vectors. So this is just capturing that kind of relationship, because the thing that we're going to have to do in order to recover this type information is perform some type inference. So as an example here, this is kind of an interesting example from some I believe actually this was also from that Western Digital device, or it was a similar IoT device. So here, so I guess actually one step back. So the reason why we want type inference. So we could manually assign types to all of the variables and other expressions that we're dealing with. But that would be a lot of work. And sometimes it might be unavoidable. And we have to, as humans, we have to add a little bit of information to make it so that our automated analyses work the best they can. But when possible, it would be much better if we could just infer the types based on any hints that we extract from our program analysis. And so what I'll show here briefly is, so these nodes, they're labeled A, B, and C. They correspond to the A, B, and C over on this left-hand side. And so these are like the type constraints that we have inferred by looking at the code in each of these nodes. In terms of notation, the one thing that I guess a couple things to point out. So the colon represents has has type of. So this is so here, for example, we say var20 has type of T3. These variables that are named T3, these are type variables or unification variables. They represent types that we haven't yet inferred. So we know that there's a type there, but we don't know what the type is. So we're giving it a variable so we can talk about what the type looks like. And then later in our next step that I'll show, we perform what's called unification, where we're taking all those type constraints, we're reasoning about them automatically, and then coming up with sort of new facts about the types that are in this program. A couple other bits of notation that are being used here. So if colon is has type of, equals is just saying two types are the same thing. So here we have two type variables, T2 and T3, and we're saying, hey, T2 and T3 are the same type. And then the last bit of notation we have is this like less than colon. And you can think of this as being, this is a subtype relationship. So we could say T3 has a subtype of bitvec32. And so what that means is if that T3 is at least a 32-bit bit vector, but it could be the things that are subtypes of a bit vec too, like an integer or a floating point number. So if these are the rules that we've assembled or that we've gathered from a kind of a cursory program analysis of this code, then what we can do is automatically, so this is the type unification part. So we have an algorithm that is able to go through and use those facts to infer type information about those variables. So what we're stepping through here is this these 4 steps here it's how we are inferring the type for this variable var20. So var20 is mentioned a couple times here in this control flow graph. So I'm just going to kind of give the human explanation of what's going on here. But the way that you would read this deduction process is we have all these facts at the top, and then those facts support this evidence that we're adding below the line. For each one of these. So for the first step that we see happening is we notice that there are a couple type variables that we're asserting they must be the same type. So T2 and T3 are the same type, and T1, T4, and T7 are all the same type. And so all that we're doing is we're updating the rules that we collected and that we had on the previous slide so that everything is described in terms of T2 and T1 rather than also T3, T4, and T7. Second step. So we see that T2 and T10 must have the same type. And we get that from looking at these 2 rules. So this is saying that we have a 32-bit pointer. In both cases, we have a 32-bit pointer that points to something. And so all we're saying is when we see this rule where T1 is a subtype of a pointer 32, that must mean that these type variables are the same. So we've introduced that constraint. Step 3, so then we know that T2 must be a subtype of C string. Because we have that T2 is equal to T10, and we have this constraint on T10 up here. That's that T10 is a subtype of C string. So then finally we get to this point where we're combining the rest of our information, or all of our information about the type variable T2. We know that's a 32-bit bit vector, and we know it's a C string of some length. So that must mean that it is a C string of 4 characters. Done. Okay, so the type inference worked, right? So this is all something that is done in automated fashion. We step through it just to kind of reason about it. But the one thing I'll point out is that even though we ended up with the C string 4 type, so a C string of length 4, it's actually not the correct type. It's close. It's really close. So it's actually a C string of 8 characters rather than 4. And the reason why we can still say the type inference works is because the type inference did the best it could with the information we gave it. It's just the problem is we gave it incorrect information. The bit that's incorrect is up here. So we say that T2 is a 32-bit bit vector. It's actually a 64-bit bit vector, but due to some ambiguities about how local variables are accessed and stored on the stack, we missed that information. So there are workarounds for that, but I just wanted to point it out that type inference works, but you also have to make sure you're giving the type inference algorithm correct information. So that's all I had for today. I just was ending on this slide again, in case you're interested in messing around with Blaze and any of the techniques we talked about today. So yeah, if there's time for questions, I'm happy to take them.
Great, thank you. So I don't think we have any in the chat. So does anyone want to either put in the chat or unmute and ask a question? Okay, well, I'll start with a question. As we talk about reverse engineering, in that process that you mentioned earlier in your talk, the whole reverse engineering idea, how do you see ways for students to get more experience trying to do kind of the reverse engineering aspect of just understanding and getting used to that as a method for discovery?
Yeah, that's a good question. Yeah, there are a lot of options. The one that we've been doing some here at Montana State is there's reverse engineering challenges called CrackMe's. So they're programs that are written intentionally as challenges, and people write very simple challenges for people that are just starting out, as well as wild stuff for people that have been around for a while and seen a lot and have a lot of experience. So finding a source of challenges, so the collection of CrackMe's would be one. Looking at reverse engineering challenges from capture the flag events is another good one. A lot of CTFs will have lots of times CTFs will have multiple sort of tracks of challenges, but a frequent one is reverse engineering challenges. And then tool wise, there are a lot of options. But one that's available for free and is definitely a competitive tool is Ghidra from the NSA. So using Ghidra using Ghidra and then trying to use Ghidra to solve those challenges would be a great first step.
Great, thank you very much. Okay, we do have a question here. That's a very interesting application. Could it be said that the problem of finding exploits could be boiled down to the binary satisfiability problem?
So I think it's, I would say it's a part of so the way I'll slightly restate it, and then see if I can use that to answer the question. So I would distinguish vulnerabilities from exploits as, so a vulnerability would be a piece of code that if you could reach it, you could perform some action, some effect. So whatever the end goal is, maybe it's like privilege escalation or something like that. Or maybe it's even simpler than that. Maybe it's just writing a byte to some place in memory that you normally would not be able to do. An exploit would then be kind of and maybe this gets to what the question was about. The exploit is really about having that path that reaches that vulnerability. And not only does it reach where execution reaches that vulnerability or the location of that vulnerability, but it's also that the state of the program is such that the vulnerability can be exercised for whatever the purpose is. So I would say it's having that satisfiable path of execution to reach the vulnerability is a substantial piece of an exploit, but you also have to have the vulnerability in the first place in order to make use of it. I hope that answered that question. If not, please.
Yeah, Noah, did that answer your question, or you want to ask another one? Said thank you. So
I've got a quick question.
Yes,
Well, thanks for an interesting talk. Graphs were central to most of the things you talked about, right? And you showed what the traditional control flow graphs or one way of looking at the program has got disadvantage and got interprocedural, right? Other than that type of nuance to looking at these graphs now, is there a way, maybe you've touched upon it very quickly, where machine learning could be used, make more use of those graphs and the way things have been abstracted to find patterns and to find structures that might be vulnerable? Is there anything you want to quickly say around the connection with machine learning?
That's interesting. The thing that immediately comes to mind is, so there certainly has been work done on trying to identify either directly vulnerabilities or using, and I've done a little bit of work in this area of using graphs as input to, say, graph neural networks to produce code embeddings. So the approach of using code embeddings to build other kinds of like classifiers or to cluster functions together that have similar structure or some similar, hopefully, right, semantics that are being captured. That's one thing. But the first thing that came to mind actually when you mentioned that is so the other big way that program binaries are kind of looked at, especially by humans, but also potentially by automated analyses, is the use of decompilers, right? So trying to go from disassembly maybe to some intermediate representation, then all the way out to something that, say, resembles the source language, so which frequently is C. There has been, I'm not that familiar on the literature that on this, but there has been some work on using machine learning to help produce better decompiler output. So that would be another connection.
Thank you. That's great.
all right, I will remind the students that there is a survey in the chat link, and we probably have time for one more question. Any more questions?
Hi, Matt. James Crabb here. Thanks for the great talk. I understand why we would use your reverse engineering from a binary, because we don't have the source code. But if you have the source code, would there ever be a reason to go through those extra steps of compiling? And then I guess to me, it seems like that would not be the case, but is there anything that going to the binary file can give us that just looking at the source code wouldn't?
Yeah. So yes. And there's actually a great paper about this called "What You See Is Not What You Execute," where they have some examples of vulnerabilities that are actually or kind of that only come about based on how a program was compiled. And it's not about the compiler being wrong. It's just there are details in the runtime that supports the execution of the program that need to be in place in order for the vulnerability to be exploitable. So there definitely are situations where having the binary or having the binary that corresponds to, so thinking about this from an attacker standpoint, right? So if you know that there is there's a machine running this program, that machine has a particular architecture. So and maybe there's details about how the program was compiled. So what compiler flags were enabled, like what optimization level was enabled. Those details can change, right? They do change that program executable, and those details can at times be critical when it comes to being able to determine whether or not that piece of software is exploitable.
Very cool. Thank you.
All right. Well, thank you very much for the presentation, and thank you for our audience. And our next talk will be in 2 weeks on April 15th. So we hope to see you all there. So thanks so much to Dr. Ravel for his presentation and for the questions. Have a great day.
Thank you.
Thank you.